Welcome back, Year 12, to your first maths topic for the year. We are starting off with the new advanced textbook for Year 12 and starting in Chapter 2, looking at graphs and equations. You will find the textbook in the OneNote, and Chapter 2 looks like this, and it refers back to this. I'm going to be starting off on 2A in the textbook, and we're going to be looking at the sign of a function. So basically within this chapter, we're looking at graphing functions. We're looking at graphing a lot more difficult functions than what you've had a look at already in Year 11. And we're basically looking at graphing them at this point without calculus. So we're looking at just some basic graphing skills. A lot of them you've seen before. We're just going to build on those from Year 11. If you're finding that what we are doing in this video or the next couple of videos, you're coming across things that you don't know, you may need to then go back to your Year 11 work and revise some of that. Noting that this current topic is going to be in our first assessment task, which is in week 8, and you'll get notified of that soon. So it's something that you need to understand really well. So go back and have a look at Year 11. If you're stuck, ask me, and we shall go from there. So the thing we're going to have a look at to start with is the sign of a function. I'm working in the OneNote. We're working through this booklet, and here's our first part here. Okay, so before we get into really looking at what we mean by the sign of a function, we're going to go over some Year 11 work. You should have known this because you would have studied this for your assessment task for the last term for Year 11. However, let's have a look at it anyway. We're looking at brackets to start with. Bracket notation. So we can write our domains or the values that our x can take in terms of inequalities. We can write them in terms of brackets, and we can also show them on a number line. So let's have a look at our first one here. We're saying it here, x has got a less than or equal to either side. So x is between 1 and 5. When we have the equal sign underneath the inequality, we can show that with a closed bracket. And then on a number line, we show that as a coloured in dot. So in this case, our values of x can be between 1 and 5, but it can also take on that value of 1 and 5. And that's what that means by it having the equal sign under it. So we close in the dots on our number line. If we were to, for our example, the second one, so that x was between 2 and 6, we don't have that equals part underneath there. They are less than. So x is greater than 2 or x is less than 6, we would show that as curved brackets or curved parentheses instead, because we don't have the equals part underneath. So x is bigger than 2, but it can't take the value of 2. X is less than 6, but it can't take the value of 6. We show them as open brackets, but on the number line, we look at them as open circles. Okay, so they're the first two examples that you may see. You may also see something where we have a combination of one of those first two types of inequalities. We've got x is greater than or equal to 5 and x is less than 10. So in this case, we're going to have a square bracket and an open bracket like this. Or if we were to pop it in a number line, we'd have a closed circle and an open circle, which is like our bottom one down here. So they're things that you should be pretty familiar with. If not, they're in our Year 11 textbook, and you can go back and have a look at those. Okay. We could also have a look at intervals which are known as unbounded intervals, in which case we only have one value, and the other value that we'd be looking at would be infinity in the either positive direction or the negative direction. So the first example here says that x is going to be greater than or equal to 5. So that means x is going to be 5 or any number bigger than 5, but we don't have an end to that value that it can equal. So we'd have infinity as the end. So we'd have 5 being the square bracket because we have our inequality sign that has an equals part underneath it. And infinity always has an open or curved parentheses because infinity doesn't end. We don't have an actual particular number that it relates to. On the number line, we would show that as a closed circle for 5, like that, and we would have it drawn like that. So in that case, x is all values that are greater than or equal to 5. And next one, x is greater than -2. We would show that on the number line being an open circle, x is going to take values bigger than that, so it's going to go in the positive direction towards infinity. So we'd have that as an open circle. Again, you should be fairly familiar with these. I'll just pop the last two in. X is going to be less than or equal to 1, so we're having a closed circle because there's an equals part under that inequality, but it's values of x less than that. So we'd be heading down this way. In this case, we're heading in the negative direction, so the values that it's going to go to would be towards infinity in the negative direction, so we'd have that as our first value, and 1 would be our second value in there. So just be really careful if you're doing these that you're popping them in the right direction. And our last one would be x is going to be less than -3. So similar to the one just up above, we have an open circle, however, we'd be heading down that way towards negative infinity. And in this case, because we don't have an equals under there, we'd have an open bracket. Okay, you should have been fairly familiar with those from year 11. The last two parts down here is if we were to look at the whole number line, which would include all real numbers, we would write that as negative infinity to infinity. And we'd also, again, we'd have curly brackets, not square brackets, because we don't have an ending number for infinity. We have another one called the degenerate interval. And we'd write this as these two A's being the same, it has only one member in its set. So if our numbers we were looking at were only the set that it contained x equal to 1, we could write that as 1, 1. I think the thing to be careful with, if we see this thing here, the degenerate interval, is that we're not thinking of it as a coordinate. That is not the point AA on the Cartesian plane, okay? That is different because that would be with curly brackets. Here it's square brackets, and we'll have a look at some questions that involve that a little bit soon. Okay, now let's have a look at this first example here, and this is where we're heading with this first exercise, is being able to solve composite functions, basically with inequalities, and we'll have a look at the graph and see what's happening here. So it says here, solve x times x minus 2 greater than or equal to 0, and write your answer using bracket interval notation. Well, before we do that, what I'd like to do is I'd like to graph this, and I'd like to solve, well, not solve, but draw the graph for this, of x minus 2 equals 0. You can all do this, so I want you to pause the video and see if you can remember how to do this. You'll be drawing this by finding the zeros for the graph, so where it cuts the x-axis. So quickly draw a sketch of that for me. Okay, so we need to find the zeros of this parabola. So we would find that would cut the x-axis when x equals 0 and x minus 2 is equal to 0, or x is equal to 2. So we've got x equals 0 and x equals 2 as our zeros of the graph. So let's quickly draw that graph. Just over here to the right. Again, we're only sketching it, but we still need to be fairly accurate with where our parts go. But I'm not plotting them per se, we're just doing a sketch. So we've got 0 here and we've got 2 here. So our graph is going to be a positive parabola, because if we were to multiply this out, we'd end up with an x squared, not a negative x squared, and it would look like this. That is a quick sketch. To be perfectly accurate, we should probably find our vertex. That would be 1 in there. If I popped x equals 1 back into my function here, I'd have 1 times 1 minus 2. So I'd have a minus 1 in here. Okay, so this should be something that you're quite familiar with from year 11, okay, with looking at the graph of a parabola equal to 0. Okay, but that's not what our question is looking at here. It's saying to solve x times x minus 2 greater than or equal to 0. Well, where is this parabola? If you have a look at the picture of it, where is this greater than or equal to 0? This is greater than or equal to 0 up here, isn't it? And up here. Okay, this is where our function, our y values, are greater than 0. So we're not looking at the part down here, because this part down here is less than 0. So we have an easy solution here. Where is it greater than or equal to 0? It's greater than or equal to 0 for values of 2 and bigger, and for values of 0 and less. So the solution would be x is greater than or equal to 2, and x is less than or equal to 0. Now you need to have the greater than or equal to and the less than or equal to, basically our closed zeros, closed circles on our zeros, because that is what it's telling us here. Okay, a point can include those zeros as well. Now, we could also write this as a union using bracket notation. So if I wrote that by looking at this part first, which is this one here, how would I write that? Have a think how we wrote that up above in our bracket notation. It looks something similar to this here, wouldn't it? So we'd have a square bracket around that first, the second part. So if I go and pop that down in there, how we would write that would be that minus infinity, oops, and I've written an 8 in there, we'll just fix that up. Minus infinity, and it would go up to 0 and include 0. And we would have a union of that, so which means it would be this part as well as the next part. So we'd have a square bracket, we'd be including that 2, and that 2 would continue on because it's all values bigger than 2 up to infinity. And that's how we would write that using bracket interval notation. That's what this is. Bracket interval notation. Now, both of these answers are correct. This one is correct. This one is correct, but it's asked us for bracket interval notation, so we want to write it as bracket interval notation. Okay, this next little bit here is not in your notes, but I thought I'd just show it to you anyway. Just a couple of other examples of bracket interval notation. For example, if we had x between 0 and 1 and x between 2 and 3, we could show that on our number line like this, okay, as closed dots. And as a bracket, we could write that as 0, 1, close brackets, union, 2, 3, and our square brackets. So if you want to pause it and have a look through here, it's quite sensible. It makes sense. We're just joining two sets of x values up with the union. So if you have a look through there, that will be something you might want to write down in your notes as well. Okay, scrolling down to your next page in your booklet, we're going to have a look at function notation or composite function notation. You might have called it function of a function last year. Pretty much the same. I note that in your year 11 assessment task, your prelims, this was not done very well at all. So I suggest you go back and you also revisit some of your year 11 work for this. Yes, it's a lot of work, but you'll need to know how to do this. We'll go through this stuff here right now, but it just generally was not done well last year. Okay, so if we have two functions, f of x and g of x, then the composite of these two functions can be written as g of f of x, which you might also see as this, g of f of x. So these are the same. Well, you might see it as f of g of x or f of g of x like this. So these guys are the same as well. So we're going to have a look at all of these different various combinations, and I'm pretty sure this is nearly the same example as we did in year 11. So we've got our function f of x being x plus 5 and g of x being x squared. So we want to find g of f of 5. Okay, so let's have a look at A. It's saying g of f of 5. So what that basically is saying is it's g of f of 5, which is equal to g of, well, what's f of 5? Well, that's popping a 5 where our x is here, which means we hop a 5 in there. So we're going to have f of x plus 5 is 5 plus 5, which is g of 10, which if we have a look up here, what's g? G of x is x squared, so g of 10 is 10 squared, which is 100. That's our first one. Okay, so B is g of 5, which means g of g of 5, which is equal to, well, what's g of 5? This part in here is g of 5 is 5 squared. So it's going to be g of 5, which is 5 squared, which is g of 25. Let's move over to the next column, which is, well, g of 25. What was g of x? G of x was x squared, so g of 25 is 25 squared, which is 625. Okay, so if you want to pause your video and have a go at them, that's fine. Otherwise, I'm just going to keep working through. F of g of 5 is the same as f of g of 5, which is equal to f of, well, what's g of 5? That is putting a 5 in here, which means a 5 in here, which is 5 squared, so it's f of 25. So I've kind of skipped a step in there. Now, f of 25 is where there was an x, we've put a 25, so it's going to be 25 plus 5, which is 30. Next one, D, f of 5. So f of 5, you must be getting good at these now, is f of, what's f of 5? Got a 5 here, so wherever our x is, we're popping a 5. 5 plus 5 is 10. So it's f of 10, which is what? It is popping a 10 there where there is an x, 10 plus 5, which is 15. Okay, let's keep going. E, g of f of x. We might change colours just so we don't get confused. G of f of x is written also like this. You don't need to write it this way if you don't like it. You can stick with this. I generally prefer to see it this way. G of f of x is g of, what's f of x? F of x is equal to x plus 5. So we have a g of x plus 5 here, and we have an x up here. So what we want to do, and this is where I think people get really confused, we had an x, so wherever there is an x, our x was squared. We have an x plus 5, so wherever there is an x, we pop in an x plus 5, and we're going to square it. So we're going to have x plus 5 squared. So you need to be really careful with that. You can leave it like that, or you could open the brackets. Either way, I quite like to leave it just like that. Okay, our next one, g of x. We can write like this. Okay, which is g of, what's g of x? G of x is x squared. Okay, so we had g of x is x squared. Now we've got g of x squared. Okay, so where we had an x, the x became squared. Now where we have an x squared, we pop that where our x was, so it's x squared all squared. So x squared all squared is x to the power of 4. Okay, 2 to go. Might change colours again so we don't get stuck. Okay, f of g of x. Let's write that like this. Okay, so we're going to end up with f of x squared, because g of x is x squared. F of x squared, we had x equals x plus 5. So wherever there was an x, we're going to pop an x squared. So that's going to be equal to x squared plus 5. Lucky last, f of x is f of x is x plus 5. So wherever we had an x, in our f of x, we're now going to pop in an x plus 5. So f of x plus 5 is x plus 5 plus 5. So it's x plus 10. So if you found any of those tricky, I want you to pause it, go back, try again, and maybe that's an alarm bell saying you need to go back and have a look at composite functions for year 11. Now your notes currently just go straight on to vertical and horizontal asymptotes. That's our next chapter. We have not done enough in here, so I'm going to jump over to the OneNote and I'll show you where we're going to go. Jump back into the OneNote. Over to the side you will see 2a sine of a function. I want to just jump into here and talk through some of these ones and some of the harder questions that are in the textbook. I probably need to change the notes that you've got. Then I don't particularly like them because they're missing out a little bit of information. Okay, where can a function change sign? Okay, so if you think of our last parabola that we looked at on our notes, going back into your notes, back up here, and we had a look at our parabola. It was positive here, it was negative here, and it was positive here. So I'm looking at where can a function change sign. So the only place where a function can change sign are where there are zeros. So if you have a look at this strange looking function over to the right, we're going from positive, I'll just use my pen here, looking at positive here to negative here, and then it's curving, so it's got a double root and it's still negative. So it's changing here one of the zeros. So that's one spot that it can change sign. The other spot that it can change sign, and we're positive here, we're still positive here, but we're jumping from a positive to a negative here, and that's a discontinuity. Okay, so the only place where a function can change a sign is at a 0 or at a discontinuity. Okay, it says recall that continuities or discontinuities, are sections of a function must be drawn by lifting the pen off the paper and creating a break. So it goes from positive to negative here and positive to negative here. One's a 0, one's discontinuity. So that's the only place that it can happen. Now we want to have a little bit of a look at tables of signs, and we're going to use that in the example that's shown below down here. Now a table of a sign can be used when we are examining the sign of a function by using a table of test values that dodge around the zeros and discontinuities. Okay, so we might look at where zeros and discontinuities happen, and we might have a look at what's happening a little bit to the left of that point, a little bit to the right, and over here we might have a look at what's happening to the left of that point and to the right of that point. And what that can do, it can tell us whether that function is positive or negative either side of that point, and we can figure out what to do when we're graphing it. Okay, we need to do one more test than the number of zeros or discontinuities present. So if we've got 1 0 here, we want to test both sides of it. So we need to test twice. Same as over here. If this is a discontinuity, we need to test either side of that point. So we're going to use that idea by having a look at this equation down here. 2a. So in the textbook, this is going to be one of the harder ones down the bottom, but you need to know how to do these, so you need to keep working through these. So I'm sorry the video is long, but I think we need it to get through this stuff this time. 2a says rearrange the inequation. X cubed plus 1 is less than or equal to x squared plus x by moving all terms to the left. So we're going to draw this function and we're going to sketch it and figure out what it looks like, and we're just stepping you through this. So if we have a look at the first one, we've got x cubed plus 1 is less than or equal to x squared plus x. So if I'm going to rearrange that by moving all terms to the left, pause the video if you need to. I'm going to get everything over to the left. So I'm going to end up with x cubed minus x squared minus x plus 1 is less than or equal to 0. So I've done the first part. Part B says factorize y equals x cubed minus x squared minus 1 minus x plus 1 by grouping. So hopefully you can see that by looking at this function here, can you see how we might factorize that? So pause it if you need to. Hopefully you can see that I can take an x squared out of this set of terms here and a minus 1 out of the second part, and it's going to work out nicely. So if I take an x squared out of the first term, I'm going to have x minus 1 left behind. I want this second bracket here, when I factorize it, to have an x minus 1. So if I take a minus 1 out of that second set of numbers, I'm going to also have an x minus 1. Likewise, now that I've got these guys being the same, I can factorize out the x minus 1, and I have an x squared minus 1 left. That is my function. Now, what does it ask me to do? Factorize that by grouping. Well, I have factorized that by grouping. I'm going to pop that back in there, and I want to find my zeros. Now, I've got an x minus 1. And what can you see about this second part here? Just ignore the minus less than or equal to 0 to start with. We're just looking at what's happening in our brackets. This is a squared term. 1 is also a squared term. So this is a difference of 2 squares. So I can write that as x minus 1, x plus 1. So I have my zeros for my graph. I have x equal to 1, 1, and minus 1 as my zeros. Now, if you were in my class last year, you should be able to graph this already. This is a cubic. It is positive. It is going to start in the top right-hand quadrant and move its way around, noting that there's a double root in there. So you should be fine with drawing that. However, let's assume you don't know that it starts in that top right-hand corner. What we're going to do is we are going to draw up a table, to C, of signs to establish where the function is positive and where it is negative. So I might pop that up here. So we're going to have our x values, we're going to have our y values, and we're going to figure out the sign, whether it's positive or negative. And I want to do that around my values that I know. So I've got a 1 and a minus 1. So let's pop a minus 1 there. I'm going to leave a little gap and pop a 1. And I want values either side of these numbers here. So if I pop a different color in, to the left of minus 1, let's just go minus 2. You don't have to pick minus 2. You could pick a massively big number. it's much easier to work with smaller ones. So I'm just going to stick to the smallest number. So I'm going to go -2. And the number between the -1 and 1, 0 is a great one to do because it's a simple one. And the other side of the 1, I'm going to pick our 2. So let's draw, let's figure out our y values for those. So we're just going to pop each of these values into our function to figure out what our y value is going to be. Straight up, we know that our y value for these ones here are 0 because they are our zeros, and that's where it cuts the x-axis. And our sign, we don't have a sign because it's 0. So we only have 3 points that we need to do. So note our little part up here said, I don't know if it was up there, it was somewhere, perhaps it was on the, oh no, here we go, on table of signs, here we go. It says we need to do one more test than the number of zeros or discontinuities. So if you have a look at what we've got, we had 2 zeros, so we're going to test 3 points. So 1 more than 2 is 3, so we need to test the 3 of them. So let's get our values in there. So I'm going to have in here -9, 1, and 3. So you need to trust me on that. Otherwise, pause it, go and pop those values of x in to your function and see what your y value is. Okay, so here, it's a negative, so our sign is negative. Here, our number is positive, and here, our number is positive. So that's part C, drawing a table of signs. Now we're going to sketch the graph, and then we're going to solve it. Now let's sketch that. So again, it's just saying sketch, so you don't need to be a perfectionist at this, but you do need to get we need to get the main points in there. And we're talking about the main points. We're talking about getting in the zeros, getting in generally where it cuts the y-axis, and if we've got turning points, we want to pop those in there as well. Okay, so our zeros are 1, 1, and -1. So what that means is we're going to have that double root at 1, and we are going to have another one at -1. So let's see if we can figure out what's happening here. So we know that we had a double root at 1. So it's either going to go this way or this way. Now, we know it's going to go that way because we learnt this last year, because a positive cubic is going to start up here. However, let's have a look what it's saying to us. So here's our x value of 1. To the right of the 1, we get a positive. So to the right of that 1, we're going to have our graph up in the positive. So we can see that it's going to go along here. To the left of our 1, towards the 0, we are going to also get a positive. So it's going to go up like this. We also know that it's going to have to turn because it's going to have to cut back down here at the other 0. It's going to be, if we have a look at to the right of the -1, it's positive, so it's up here. To the left of the -1, it's negative, so it's going to go back down here. So it's going to go through like that. There are our 2 main points, but we want to figure out, well, where does it cut the y-axis? It cuts the y-axis when x is equal to 0. So if I pop zeros in all of those, I'm going to get a 1 up there as well. And I could also find some other information, but I think that should be enough for us for now. Okay, so we've sketched that graph. Now let's have a look at part E. It says from the graph or from the table of signs, find the solution of this here. Okay, so that's what our end point is to find that solution. Now we've rearranged this function here to be this here. Okay, which is what we've plotted. So we've actually plotted this part here. Okay, but we've plotted it so that in our brains it sort of made a little bit more sense to think of it like this. Okay, this part here has become this. They're the same. We've just used algebra to get from one form to the other. But what we want to do is look at where this graph, or this function, these being the same, and this being the algebraic form, this being the graphical form, where is it less than or equal to 0? Now, I reckon most of you are going to say, yep, there, you're spot on, but you're not entirely correct. Where else is it less than or equal to 0? There as well. Okay, if that was missing, this part, and it was just less than 0, then we'd want only that part of the line here that was less than 1, but it also equals 0 at that point there. And that's the one that I think a lot of people will end up forgetting. So our solution is x is equal to 1 and x is less than or equal to -1. Are our solutions. Okay, and we could also write this in bracket notation as 1, 1. This being the point 1, not the coordinates 1, 1 on the Cartesian plane, because that would be rounded brackets. And this would also then be minus infinity. Oops, I keep writing them as 8s, don't I? Sorry. It's crazy. Minus infinity and minus 1. Okay, so I'm sorry this is a really long video. You might want to stop it here, go back and have a look at the exercises, and then when you get to ones that are a little bit trickier towards the bottom, come back and rework these videos. However, I'm going to keep going. So there's one more to go, and I want to examine the sign of y equals x minus 1 over x minus 4. If you're looking at the textbook, these would be things that are similar to 19 in exercise 2a. Probably not wanting to go too much further than that. We've kind of looked at ones like 21 already, actually, which would have been the last one. So similar to 19. So let's jump in and have a go at that now. Straight up, what do you see? You should look at the bottom and know we can't divide by 0, so you're going to have an asymptote or some form of discontinuity or something at x equals 4. Okay, we'll say discontinuous asymptote. That's the first thing you're going to notice, hopefully. The second thing is, well, we can't really find the asymptotes to go the other way yet. Okay, so this is a vertical asymptote. We haven't looked at horizontal asymptotes really yet. That will come soon. What about zeros? Cuts the y-axis when x is equal to 0. Cuts the x-axis when y equals to 0. So let's pop y is equal to 0 in there. This is where it cuts the x-axis. Y is 0. So if I pop y equals 0 in there, if I multiply both sides by x minus 4, I'm going to get 0 equals x minus 1. So x equals 1 is a 0. So we've got 2 points that are important to start with. An asymptote and a 0. So the question wants us to examine the sign of this, so we need to pop a table in there, and then we can graph it with the information, hopefully. So x and y, let's pop the sign in. We've got 2 points we know about. X is 4 and x is 1, so let's pop those in. And we need some points either side, so let's just find ones right near it. So to the left of 1 would be 0. I'd probably just pick to the right of 1 being 2. And we need one bigger than 4, which is 5. You could pick 3 instead of 2. I don't mind. I'm picking 2 because it's easier. The sign, sorry, not the sign, the value is smaller. So it's just going to make the maths a heck of a lot easier. So if we pop those x values into here, we're going to get the y values. We know that when x is 4, it's discontinuous. So we don't get a value for y. So there's nothing there. Nothing's in there at all. There's no value. You can put a star or an n for nothing. When x is 1, it's 0. It's where it cuts the y-axis. Okay. Sorry, it's where it cuts the x-axis. And at that point, y is nothing. Sorry, I'm really having a shocker here, I know, at the moment. I'm putting it in the wrong spot there. And there we go. It's nothing there. And our sign is nothing. There's no sign. It's on the axis. So we need to pop in 0 and 2 and 5 into here one by one to get our y values. And those values are, end up with 1/4, minus 1/2, and 4. So 1/4 is positive, minus 1/2 is negative, and 4 is positive. Let's see if we can draw it. Pop a little axis over here. I like to put my x's and y's on. What do we know? We know there's an asymptote at x is equal to 4. And we know there's a 0 at x is equal to 1. Looks to me like it's going to be a hyperbola, okay? And it's going to be a positive hyperbola, so you're probably going to find without doing anything that you're going to have one part down here and one part down here. If it was negative, would it be in the opposite corners? We know it's a positive because the x's do not have negatives out the front of it. But let's check and see what's happening anyway. Okay, so I'm going to start over here. I just like to start on the right-hand side. So we've got an asymptote at 4. We know on the right-hand side of the 4, we're in the positive side, so we are up here. So it's going to be like that. And we know that to the left-hand side of 4, we're negative. So to the left-hand side of 4, we're down here somewhere. Okay, so it looks like my guess was right there. 1 is a 0, so it's going to cut there. So it's either going to go that way or that way, which we know it's negative down here, so it's going to go through there. And we know to the left-hand side of that 1, it's positive. So yeah, so the left-hand side it's positive, the right-hand side it's negative. So it's going to look something like that. The only other thing we don't have on there is this little point here. It cuts the y-axis when x is 0. So if I was to pop a 0 in here and in here, I'd end up with a quarter up there, which is what that y value is there. Okay, so that's that done. We will look at this in heaps more detail anyway in the next few lessons. Thank you.